Hey guys, welcome back. In this video, I'm going to be providing a brief review on simple linear regression. The focus of this class is multiple linear regression, and I'm doing this video for some of you guys that might not feel comfortable yet going straight into multiple linear regression because you haven't taken Stat 5615 or some other probability class that you at least talked about simple linear regression. With that in mind, I'm not going into all the details that I would normally do if I was teaching this in maybe an intro class. This is just to give us a baby step into multiple linear regression for those that are nervous going into a topic. So let's get started. So far, we've done design of experiments, and in that case, we have had factors that are discrete or groups. Now what we're going to be talking about is when we have two variables that are continuous. So our x is continuous and our y is continuous, and we want to understand that relationship between those two variables. In multiple linear regression, as a foreshadow, we're going to have multiple x's or explanatory variables. So here's a simple example where a chemist is going to run a chemical process several times in order to understand the relationship between concentration of a certain catalyst and understanding the yield up from that. And so this experiment is going to generate bivariate data. So we're going to collect x1 and y1, x2, y2. Both x1 and y, or x's and y's, are observed. So in our experimental designs, we were applying some treatment or some factor, and then we were getting our response y. Okay, some terminology that I might be using is here, or you might hear in stats in general. We have a response variable, which is the outcome of the study. That's the y. It's kind of what we're interested in looking at and understanding how it changes with respect to our explanatory or our predictor variables. I also might say covariates, regressors, predictors, and these are all about explaining in what influences the response. Right now, we're going to be only focused on one explanatory variable. Note that we try not to use the terms like independent and dependent, because in stats we do have meanings in a different way. Typically, I know I mentioned it once in your multiple linear regression to hopefully make a connection from something that you might have seen before. But typically we don't use independent and dependent variables that you might have seen in high school because they do have a different meaning. Here, this is just, again, saying that experimental designs, we had a clear response because we were controlling the predictors, and observational studies, we are not controlling. All we're doing is observing, and here's a couple of examples. So the number of, or the inches of rain in a growing season and the yield of corn. Unfortunately, we can't control the rain and when it comes and how much it comes. So we're just observing how much rain and how much yield. The weight in kilograms and the height in centimeters of a person, we really can't control that either. And then number of hours spent doing homework and the grade a student earns on an exam. Unfortunately, as teachers, we can't really force you to spend a certain number of hours or put that as a treatment. And so all we're doing is observing that. Typically, when we have two numerical values or variables, we do a couple different things. We look at the scatter plot to see what kind of relationship or direction or the strength. We also can look at see if there's a linear association between the two variables to see if they're correlated. And then we also look at determining if a linear model would best explain this relationship. For this kind of brief review on simple linear regression, I'm not going to worry about these two. The reason why, making scatter plots, that should be a dead to right first thing you do when you get your data. No matter what your data is, you should always be plotting it, even if it's categorical, to understand what's going on. Sometimes a picture is worth a million words, is the common saying, I believe. Um, and when you are looking at those scatter plots, looking at the relationship, if you see a parabola relation or a parabola type relationship between your x and y, a simple linear regression will not be beneficial because a simple linear regression is just going to be making a line. So just using some intuition, plotting your data. Where we're going to be focused on is looking at how we're going to make a linear model that's going to best explain a relationship between these two variables. Okay, so that's where we're going to get started and get going. So the idea of regression models is a very big thing in stats. The whole idea is that we want to create a model that's going to help us understand how our variables are related. So we have these x's or we have these explanatory variables, and we want to understand how that's going to impact our y or what we're interested in. Regression models are a super large topic. In this course, we're going to be focused on simple linear regression and multiple linear regression, but that's not where it stops. There's a lot of different regression models, GPs, splines, all that type of stuff. We're just not going to focus on it. Okay. But to motivate us and understand why we need models, let's go to a simple kind of common example we see. So let's say we're trying to predict someone's GPA, their college GPA from their stats SAT score. That's our goal, is to be able to make a prediction. Okay, so the first thing I do is I plot my data. I look at it, seems pretty linear, we're going to keep going on it. But the idea I'm going to try to convince you here is, let's say we don't know anything about models, and someone comes up to you and says, I just want to best guess off the top of your head, what would you predict overall? And potentially overall, hopefully you guys might think we should do the overall mean. And so that's what I have in this plot right here. This dashed line in your notes is red. Colored printer isn't working right now. And so without any knowledge or any model influence, the best guess we could give someone of someone's GPA based on their SAT might just be the overall. Okay. Now, from our design of experiments portion of this class, hopefully you guys remember the fundamental idea we started off with was we have a total variability in our design. And then we broke it up into different systematic and random background noise. We're going to keep the same idea here with regression models. And so we have this similar idea of, we have that total sums of squares, which is going to measure our overall kind of total variability. And what that is, in terms of our regression model, is it's going to measure the distance between what we observed and our overall mean, squared. So if we took this distance here, and then we squared it for every single one, that's going to represent our total variation. Okay. Now, the idea with simple linear regression is, can we find some type of line? Maybe it's this, maybe it's a line like this, maybe it's a line here, or here, or here, that best helps us to understand the relationship between X and Y. Okay. So that's where we're going towards. Is we want to find this fitted regression line that is going to help us best explain our data. So in a simple linear regression, our statistical model looks something like this for each of the individual eyes. Beta naught and beta 1 are going to be the true regression parameters. Again, to us, these are unknown and we will have to estimate them. And then we have this random error assumption, or our residual error. Okay. There are some assumptions that go into this, and what this is saying is that our sigma squared is constant along the line We have constant or homogeneity and our variance. This is an assumption we will have to check later on when we talk about assumptions for multiple linear regression. The whole idea of this error term is that in the most ideal situation, we have no variability in our data and we can exactly predict what our relationship is. That's the most ideal. We can always predict it. Realistically, that's not true. And so we need some type of error to help us understand that. Okay. So now our goal is here's our model. And hopefully you've started to realize here's our parameters. We have to estimate these somehow. How we are going to do it in simple linear regression and multiple linear regression is a technique called least squares. And it's going to give us the best, and I'm putting best in quotes because what does best mean? Well, in our case, it's going to mean minimizing the sum of squares error. But best could mean a lot of other things, and there could be maybe a different estimate that you want to use. But for our case, we want to talk about the least squares regression line. Okay, so the whole idea is we are going to get predicted values, which we represent by y hat, and we get estimates for beta naught and beta 1. We're going to get these values by minimizing the difference between what we observe and then the fitted line. Let's get a picture in here. So the whole idea is our least squares regression line is going to output a line like this. Now note, just with this data, there are a multitude of lines that could pass through the data. For instance, my pen could be another line through this data. It really wouldn't make sense because it's not representing our data, but it could be a line. And so the whole idea of the least squares regression is it's going to sit here and find the line that's going to minimize the distance between what we observe and what we're predicting for each one. So this line right here is the line that minimizes what we call the residual distance. Okay. All right. Now, I want to go briefly back because at the beginning of this lesson, I was talking about how we break down our total sums of squares into sums of squares regression and then sums of squares error. In our completely randomized design and like maybe our randomized complete block design, we would have the sums of squares treatment, the sums of squares blocks. But in simple linear regression and regression, we're breaking it down into the variability explained by our model or our regression line, and then the variability explained in our error or residuals. So that's what's going on here. What this sums of squares residual is looking at is this is looking at the difference between our blue predicted line and our overall mean, which was highlighted in pink and red on your paper. So the sums of squares regression is looking at this difference. Now, you can hopefully notice that if I take this line from being here and I start to move it closer to the overall mean, this sums of squares regression will get smaller. And so our predicted line, as the sums of squares regression gets smaller, this predicted line isn't going to do any better than just doing the overall mean. But as this line gets further away and we get a larger sums of squares residuals, then it's saying that our model or our line is explaining more of the variation in y. Our sums of squared error, again, is this residual distance right here. And this is the quantity, right here is the quantity that we are going to try and minimize to find those values of beta hats that got our blue line above there. If you're interested in how exactly that's computed, what we end up doing is taking the derivative of the sums of squares error with respect to betas. And I have it written out here for those that are interested in it. So E, you might see this in some literature or other people's notes. Some people represent residuals by a lowercase ei. We're representing the same thing. But the whole idea is that we want to minimize. These should not have hats. Wait, no, we don't want these to have hats just yet. Hats come on once we've estimated. You could leave them on, but here or there, whether they I would typically wait until down here once we get the quantities to estimate them. Personal preference, you can keep them on if you want. I'll probably keep them on your notes so I don't have to reprint these. Okay, back to what I was saying. So your sums of squared errors can be written in terms of beta 1 and beta 2. To find the values that would help us, we're going to minimize the sums of squares with respect to beta 1 and beta 0, do some algebra, and then you find that they're these values. Here's the thing for our class. You don't need to know this. You can put it into JUMP or R and calculate it that way. But I figured I'd put it here for those that would like to see it. So in our SAT GPA example, if you use JUMP or R or whatever software you prefer, you can see that our estimates for beta 1 are 0.003, beta naught is minus 0.6, and so our regression line is this. All right. Now, our thing was, for our data, we just created this line. Now we need to look into some way to assess how well this line fits our data or tells us about our data. And so that's what we're going to look at right now, is kind of a goodness of fit statistic. Okay, and this quantity, a goodness of fit statistic in general, is going to measure how well a model explains the given data set. What we're going to talk about is coefficient of determination, which is also known as R squared. R squared's more the common idea, which is the sums of squares regression divided by total sums of squares, which is a measure of how much variability in Y can be explained by our regression of X onto Y, or the model. Hopefully this makes a little bit of sense from our intuition of what sums of squares residual is, and the fact that sums of squares residual is comprises the total sums of squares, which I keep writing as SST in this lecture. I don't know why. So when your sums of squares is large, we have a large amount of variation in Y with our regression model. So if we were to apply this to our GPA SAT example, we would find that we have an R squared of 0.43. How we would interpret that is that this is, how we would interpret it is that this is approximately 43%. So 43% of the variation in GPA can be explained by the regression model within SAT as the predictor. The rest of the variation is due to random unmodeled noise. Okay. Now, something else you might want to also understand and make sure to get an idea before you going into multiple linear regression is interpreting the least squares regression line. So here's a different example in which we have data. And the whole idea was that we already created this line right here. This is our predicted line. And we found that our y is equal to our intercept minus this slope, and this is the x. And so we want to be able to interpret these. So our slope should seem familiar back to algebra when we were trying to interpret x and y equals mx plus b. So how we would interpret this would be, it's going to tell us the fat gain is going to go down because our slope is negative by 0.00344 kilograms for each added calorie in ENA. So the slope is going to tell us the expected rate of change in the responsive variable as the explanatory variable changes. In multiple linear regression, this interpretation changes slightly, and the fact that you need the extra clause of given that the rest of the explanatory variables are constant. We'll get there, and hopefully I'm trying to foreshadow a little bit as you move into multiple linear regression. The intercept is interpreted as if your x was 0, what would that be? So in this case, if any NEA doesn't change when a person overeats, that's what your 0 is going to tell you. If your intercept, so the intercept should only be interpreted if it's in the interval of the study. So in this case, 0 calories makes sense. In the fact of our GPA example, SATs don't go to 0, so it doesn't make sense to interpret the beta naught in this case, but we still need it in the model. We would also interpret our slope as for every increase point in SAT score, a student's GPA will increase by 0.003. It's going to increase because we have a positive slope. The whole idea of not interpreting our intercept in our SAT example kind of goes to the idea of extrapolation and interpolation. So extrapolation is when we kind of make predictions well outside the range of the explanatory variables that you use to obtain a line. And interpolation is when you make some type of prediction within the range of the variables. So interpolation is good, extrapolation is bad. Why would extrapolation be bad? Because it's because we only know and relatively understand the relationship of our x and y in our specific range. We don't know what's going to happen outside the range. So in this example, we have data from the ranged from here to like roughly here, and it looks linear, but we don't know how it's going to behave after that. And our model can't help us really because we don't have data out here. It's a mystery. This is going to also come into play when you make confidence intervals and prediction intervals, because you wouldn't want to make confidence intervals and prediction intervals also outside of your range. With that in mind, let's talk about those, because that's something we're going to also talk about in multiple linear regression. And the whole idea of confidence intervals and prediction intervals is that we developed a line of best fit. If we go back to this picture, this is this is what we're estimating because we were using beta naughts and beta 1/2. And so we have an estimate, and now we want to create a confidence interval around it. The idea of the confidence interval is that we have a mean, i.e. this predicted line, and we want to create a confidence interval for each point maybe, which would help us create a confidence band. And so what we're going to do is we are going to find the confidence intervals values for the individual fitted values of y hat for a particular value of x. What the next part of notes is going to do is going to kind of bring you through the more of the probability, expectation, variance, distribution aspect of confidence intervals. You guys don't have to worry too much about this. This would be a typical approach that I would expect to make sense if you had already taken Stat 5615, you understand expectations and all of that. I'm not going to spend too much time here with it. What I do want you to understand is that a confidence interval is for inference on the mean response, okay? Whereas our next thing called prediction intervals is for an individual future response. So we're no longer interested in quantifying the uncertainty of the average or the mean. We're interested in understanding the uncertainty for predicting a future value of y for a given new point that I might denote as x star or x naught. I kind of flip between the two. Sorry for that. So the whole idea is for a new x star, the estimated or predicted value would be given by this equation, i.e. we're just going to put our x star in here and we'll get our y hat star. Our predicted value for our estimated predicted value for the prediction interval, i.e. the y hat star, and the inference for confidence intervals will be the same. What I mean by that is our fitted line, the blue line we've been seeing, will be the same. What's different is the uncertainty around it. And without going into too much detail, pretty much what happens is trying to understand this new extra observation is going to increase our standard error. The best way I could explain the difference and increase in uncertainty between prediction intervals, which is for a future observation, and confidence intervals on the mean response is through this analogy. Let's say you're in a group of friends and you want to try to predict the average GPA of someone in that, or the average GPA of the overall group. You have some indication of how smart your friends are. We're going to say our friends are pretty smart and and together our average GPA is a 3.5. All right. It's easier to kind of come up with an average guess for everyone. But now if one of your friends goes, well, you're smart, guess what my GPA is? That's going to be a lot harder to guess. So guessing an average of a group is easier than guessing a single individual person. So that's kind of the intuition a little bit behind this. For this class, you guys won't need to understand too much about this theory and these equations. What I would expect from you guys is understanding both the confidence and prediction intervals have the same prediction mean, i.e. this blue fitted line that we saw before, but has different bands. And so here I plotted the prediction intervals and the confidence intervals. The confidence intervals are represented by this dashed line here and here because we have an upper and lower. Notice that as we get towards the end, the tails start to flare up. That's because we have less data and we're starting to go into those areas that we don't have as much data. The prediction bands or intervals are always going to be bigger and they're going to be represented by these pink lines right here. So this is a common question I ask on homeworks and tests. is between the confidence and prediction intervals, which one will be larger or which one will be wider. And prediction intervals will always be wider because you have that extra bit of uncertainty. All right. The next couple of points I just kind of want to throw out there because they would be something I would cover if the class was kind of ending on simple linear regression, but this class is almost assumed that you've done simple linear regression in a previous class. There are some things that you can transform your data. So typically in biology, this is kind of one of my favorite examples. We're looking at weight of the body and weight of the brain. And we kind of have some of these outliers with elephants and hippos and dolphins and humans. And what you can do is you can apply a log transform. Typically, when I say log transform, it's known to be the natural log. I would definitely go through your literature and make sure that it's not log base 10 or something weird. In this class, if I ever say log, always assume natural log. And so in this case, what we ended up doing was taking the log of the body weight and the log of the brain weight over here. You can also only just transform the response variable, so that y, if you choose so. So this is the original, this is now the transformed, I think. Yeah. Also, another big thing that we will talk about when it comes to multiple linear regression is outliers. So here, what we have is we're going to be looking at subject 16. What this picture is trying to do is say, okay, we fit the model with data. Now, if we remove this point, look at how much, it's this dotted line right here, the regression line changes. It doesn't really change much, mostly because that's not really an outlying point. However, if we took subject 16, so we took this point and we dragged it all the way down here, and we then refit our data, our new least squares line would be something like this. And so this outlier is heavily going to impact our simple linear regression line. And that should make sense because of how the estimates for that line are made. They're made by minimizing the sums of squares residual. Okay. One thing I have to say about outliers that I don't think said enough, and this could maybe be my personal opinion, when you have an outlier, please don't just automatically throw it out. Typically, outliers are where the cool stuff comes from. I mean, a lot of my research is trying to detect anomalies, and once we do, it's all about figuring out why that anomaly occurred. Is it a true anomaly? Is it something wrong with our mechanism or whatnot? So I think outliers are really where research thrives because it tells us where things are going wrong or whatnot. So don't just throw out an outlier. Go investigate it. Make sure it's not just a clinical or a clerical error where you misput the decimal point or whatnot. Really investigate it. Make sure it's what it is. The last thing would be there are assumptions and conditions for simple linear regression. Again, I'm not going to go too far into this because I will be talking about assumptions for multiple linear regression, which do boil down to very similar things, which are the error isn't normally distributed. We made that assumption about the error, and we would expect that assumption to hold for us to do regression. We also made an assumption that the variances, so make sure, these points are what violate simple linear regression. So we want simple linear regression to have variances that are constant. Where this assumption comes out is, again, that epsilon normal 0 sigma squared. So we expect our errors to be normal. We expect them to have constant variance. We want our observations to be independent and not dependent. If your data is dependent on time or space or has some type of covariance structure that's important, this might not be the case. Probably don't want to apply this method. You also want to look for outliers, make sure you investigate them. And then the rest is just how you would check them, check these assumptions, but we will go through that for multiple linear regression. Yeah. So I know that was probably a lot in a hopefully short amount of time. I got to go look back at the time for this. But it's just to give you a rough idea of what simple linear regression is so you feel comfortable moving into multiple linear regression. Again, we didn't cover everything. Something we will be covering in multiple linear regression this week is testing, and we didn't even cover testing in this case. But with that, I think you should be good to go with at least having an idea of what simple linear regression is and moving into multiple linear regression.